quickly over two of the problems that I assigned. And so the question is always the same. And that's what you're going to get on a test, on a quiz and so on. Find the orthogonal matrix that orthogonally diagonalizes this matrix, and find also the corresponding diagonal matrix. And this can only work for symmetric matrices. Okay, so step one. So it's basically the same as what we did with diagonalization, except we do this one extra step, this so-called normalization. I'll show you again. Okay, so the characteristic equation. We have 3 minus lambda, 1, 1, 3 minus lambda, 0. So that is, it's product of the diagonals, 3 minus lambda times 3 minus lambda. What is going on here? Okay, I'm going to write it here. There's something jumping here. 3 minus lambda square minus 1. Okay, and then double product formula, that is 9 minus 6 lambda plus lambda square minus 1. If you do, you can FOIL it out. Lambda square minus 6 lambda plus 8. So two numbers that multiply to 8 and add up to 6, 2 and 4. So we get lambda equals 2 and lambda equals 4. Okay. So step 2, eigenspace for lambda equals, I'll do lambda equals 4 for a change, to see that you don't always have to do the same. Okay, so we do lambda equals 4, plug that in here, we get minus 1, 1, 1, minus 1, right? Yes, okay. I need to get rid of this, so I'm going to do row 1 minus row 1. We get 1 minus 1, 1 minus 1. And of course, we see that since the two rows are the same, we get row 1, row 2, replace that by row 2 minus row 1, and you get 0. Okay. So we get 1 minus 1 and then zeros. Let's see, this gives x1 is the pivot variable, x2 is the free variable. So if you write x1, x2, x2 is always equal to itself, it's a free variable, and x1 is equal to x2 also from this equation. So we get x2, 1, 1. Okay, so now the extra step is the normalization. Now we have to normalize. So we take the norm of this guy, 1, 1. That would be radical. There's always the radical norm, right? You take the square of the entries and add them up. So this is radical 2. And so then our basis, the full correct way is, I'll write it up for you, orthonormal basis. And you see the ortho refers to the fact that at the end we will have an orthogonal matrix, that the columns, different columns are orthogonal, and the normal refers to this process we just did. Okay, so the orthonormal basis is 1 radical 2, 1, 1. Now we're going to have to put this in the matrix, so sometimes we just write it that way. And never rationalize, there's no need to do that. The eigenspace for lambda equals 2. Okay, so we subtract 2 from the diagonal, is 1, 1, 1, 1. We do row 2 minus row 1. We get 1, 1, 0, 0. So very quickly, this is going to be our free variable. So I did and this is going to be the pivot variable. So x1, x2. The pivot variable is, the free variable is equal to itself. Sorry for the colors are a bit wrong, but okay. And from this equation we see x1 is minus x2. So here we always have to have the free variable, right? So minus 1, 1. So the extra step now is we normalize. So we have to take the norm of this fellow, which is the square of minus 1, that's just 1. Square of 1 is 1, so again radical 2. That they are the same is sometimes coincidence, so we don't read too much into it. And so the basis that I consider now is 1 radical 2 minus 1, 1. Or if I want to write it all in one single column, is this. Okay, so step 3, let's go back to back. Step 3, we are done. this is now, we put everything together. P, our orthogonal matrix, is now obtained by getting these two basis vectors in there. I'm keeping the order that I have, so it's 1 over radical 2, 1 over radical 2, minus 1 over radical 2, 1 over radical 2. Oh, sorry, that's not what I meant to write. But then what's the corresponding d? Let's write this here. The corresponding d, well, the first one was for eigenvalues 4, and the one for 2, right? So 4, 0, 0, 2. Okay, good. Let's now, so what does this mean? This means that if we take, when we diagonalize, this is what we do, right? We find a matrix that is similar, but this is an orthogonal matrix. So this is now an orthogonal matrix, and this means that P is equal to the inverse of P is equal to the transpose of P. So instead of writing an inverse here, I can, I can write here transpose, because it's much easier to find the transpose of a matrix, just flipping everything around. So this is the equation that this says it's true. Let's double check it, because it's not so hard, as I said. So okay, let's write down the transpose of P first. So this is P, so the transpose of that is 1 radical 2 minus 1 radical 2. I write the rows as columns. 1 radical 2, 1 radical 2. And we have 4, A. What was A? 3, 1, 3. And then we have 1 radical 2 minus. Now it's the P itself. So this is P transpose, this was A, and this is P. Okay, 1 radical 2, 1 radical 2. Now this might, and what we need to get is this one. So this might be a little bit cumbersome because of these radicals in there, but these are scalars. And so out of this one, I can factor out 1 over radical 2. And out of this one, I can factor out 1 over radical 2, and I can bring these both outside, in front. That is because we can do this with scalars, with just numbers. We cannot do this with matrices, we can do this with the numbers. So what we're left with is therefore this times this times this. And that, of course, is much easier to calculate. Now, this is a half. So let's calculate the first two together here. A 3 plus 1 is 4. I'm doing the rows first. Then a 1 plus 3 is 4, second row. Minus 1 plus 1, that is minus 2. Minus 1 plus 3 is 2. Right? Yeah, okay. And now I have to both 1 minus 1, 1, 1. It's a half, don't forget that half there. First row. 4 plus 4, that is 8, minus 4 plus 4 is 0, minus 2 plus 2, I'm doing row 2 now, and then finally the last element is minus 2 plus 2, that's 4. And a half of this is exactly 4, 0, 0, 2, the diagonal matrix. Okay, so let's do one more here, number, what was it, number 16? Yeah, number 16. I hope you understood what I was asking here. I just want to do the same question with that matrix. Okay, if you didn't get that this is what I wanted you to do, stop the video now, do it, work it out, see whether you can do it, and then look at the solution. Okay, so step 1, this is symmetric matrix, right? Okay, so that makes sense. Okay, characteristic equation. We have 6 minus lambda minus 2 minus 2, 3 minus lambda equal to 0. So that is 6 minus lambda times 3 minus lambda minus minus minus, so this is minus 4. Yeah. Let's fold this out. 18 minus 6 lambda minus 3 lambda plus lambda squared minus 4. So we get lambda squared minus 9 lambda. You add the like terms and then plus 14. So these factors, two numbers multiplied to 14 add up to 9. That is 2 and 7. Okay, so this is lambda equals 2. This is lambda equals 7. Okay, so step 2. Let's do the eigenspace for lambda equals 2 first. So we subtract 2 from the diagonal, get 4, negative 2, negative 2, 1. Yeah, here you see I have to get some fractions. So I'm going to do row 1, 1/4 of row 1. It gives me 1 minus a half, and then minus 2, 1. So now I get a 0 in the bottom by doing this, plus 2 times row 1. And of course, what you need to happen is not just a 0 here, but also a 0 there, which is the case. We need a 0 row so that we have 1. This is the pivot variable, x1, but we need a free variable, which we have, that's x2. So x1, x2. x2 is itself. What is x1? Well, it's a half x2. Sorry, x2. Everything has to be in here. At the final part, you can only have free variables, and then you can factor them out. And of course, in this case, it's exactly one free variable and exactly one pivot variable, right? But in larger sizes can be different things. A half 1. Okay, and so we can now normalize this one, but we don't need to normalize this particular one because the fraction might be a little bit awkward to do that. So it's up to you whether you like it to work with fractions or not. So, because why can we do this? Well, we have said any element in here is a basis vector. Because what is this? Well, this is all the vectors, multiples of this form a line, right? It's a line, all the vectors that line a certain line. And there is only one unit vector, so they form kind of a line like this. And this exactly, here's the origin. My drawing is very vague, right? So this would be my unit vector. And there's only one unit vector, no matter which one I start, they will all these vectors here, all this vector and this vector, they all will have the same unit vector, this one. Okay, so that's why I can choose what I want. So meaning to say I'm going to take x2 equal to 2 here, so that I get my basis, I get 1, 2, and get rid of my denominator. So, okay, let's take now, so we still have to do the normalization, right? I didn't do that. I just picked something that was nice. Now I have to normalize. I'll make it nice again because it's going to get, radicals in there and fractions. But okay, 1 squared plus 2 squared, so radical 5. And so our basis, or orthonormal basis, but I'm just going to say basis, is 1 over radical 5, 1, 2. Right, it's this one, right? Sorry. Yeah, you have to stick to the one that you're dealing with, right? So we took that one, so we now take 1, 2. And since we're going to put this in the matrix, I'm just going to bring the radical inside, also fraction. Okay, and then the other eigenvalue is lambda is 7. Yeah, lambda is 7. Lambda is 7, so we have to plug in 7 in here. So we get a -1, -2, -1, -2, and a -2, -4. -2, -4. Good. Yeah, we need to have a +1 there, so I'm going to do row 1 minus row 1. I get 1, 2, -2, -4, and then I do row 2 plus 2 times row 1. I get 1, 2, 0, 0. I have to get a 0 here, so again, I keep my colors here. This is x1, the free variable, and x2 is the... Sorry, x1 is the pivot variable, x2 is the free variable. So x1, x2. The free variable is equal to itself, and from this equation I see that this is -2 times x2. So I get x2 -2, 1. And this is, I'm happy with this one. I don't need to take a multiple. I can if I want to, but why? Okay, so I'm going to take, now I have to normalize. So this is the extra step, right? This is because we're doing orthogonal diagonalization. This is the part that's new. So we do this one now, -2, 1. That's the square root of -2 squared, that is 4, 1 squared is 1. So again, square root of 5. Again, I told you, it's not always the same, that you're not always going to get the same answer here. Although very often you do. Good. Yeah, and so what is the basis? The basis now is 1 over this number, right? Times the vector that we were working with, this one. So it is -2 radical 5, 1 radical 5. So, good. So step 3, or final step. What is P? What is D? Well, P, we put in just the basis vectors that we found. This is the one there, 1 over radical 5, 2 over radical 5. And the new one was -2 over radical 5, 1 over radical 5, okay? And the corresponding eigenvalues were 2 and 7. 2, 0, 0, 7, okay? And we can, again, do the same trick here. I'll do it very quickly. So remember, this should be true. So this is, I say, check, but this is not part of the question anymore. You don't have to do that, but you can just check. Remember, I write transpose here because normally it's inverse, but we are orthogonal matrix, so that's what it comes. So we get the transpose of this matrix is 1 radical 5 minus 2 radical 5, 2 radical 5, 1 over radical 5. Then we have A itself, which I kind of forgot what it was. 6 minus 2 minus 2, 3. 6 minus 2 minus 2, 3. And then the P itself, 1 radical 5 minus 2 radical 5, 2 radical 5, 1 radical 5. So again, I'm going to put the radical 5s out, both of them. That makes it much easier to work with these things. Okay, and let's now multiply. This is 1 over 5. I'm going to do these two first now, just to show that you can do whatever you want. Of course, you cannot mix them around, right? You cannot shove them around, but you have to do it in the order they are given. So the first element here on top is 6 minus 4. Then it is minus 12 minus 2. In the bottom, you get minus 2 plus 6. And you get 4 plus 3. Okay, so we get 1/5. And now the first row is 2 plus 8, that's 10. And that is minus 14 plus 14, that's 0. Good, good, because it has to be a diagonal matrix. The second row, minus 4 plus 4, that's 0. And then we have 28 plus 7, that's 35. And miraculously, everything falls exactly into place and we get the diagonal matrix that we were supposed to have. Okay? All right, so we are ready for a quiz for this thing. So on a quiz, but I'll do a review of it. So what I also might ask is, now that you are this far, well, calculate now the 5th power of A or something like that. And that's the same principle as we did in the previous case. Okay, but I'll do a review for that.